So the last thing I'm going to say is something very quickly about the simplest method I know for solving differential equations. And many of the equations I've written down in this podcast you'll recognise are first-order separable equations. Now, a first-order separable equation is of the form dy by dx, this is rate of change of y with respect to x, can be written as the product of some function of y times some function of x. So this is called a separable equation. And so what do you do to solve it? Well, the first thing you do is you get all the y dependence over to this side. So we divide through by f of y. And this way I'm going to do is the posh mathematical way of doing it. And then I'll show you the quick and dirty method. So 1 over f of y dy by dx is equal to g of x. Now, if we're going to do this technically correctly, what we'd say now is we'll integrate both sides of that equation with respect to x. So we write down the integral of 1 over f of y dy by dx, that's the left-hand side integrated with respect to x. That's equal to the integral of g of x with respect to x. And then finally, on this left-hand side, we'd recognise that this is equivalent to a substitution integral, so we can change variables from y to x from x to y in the integral. And so this left-hand integral becomes the integral of 1 over f of y dy, and the right-hand side stays the same. Okay, and if you can do this integral here with respect to y, and you can do this integral here with respect to x, then you can solve this differential equation. And every time you integrate, you must remember that you have an integration constant. Well, that's the long way of writing it down. The quick way of writing it down is just to pretend that actually that this is a fraction. It's not a fraction, it's a differential operator. But you can pretend it's a fraction just for the sake of rearranging this to get to here. So what we do is we take all the y parts over to one side and all the x parts over to the other side, and just write 1 over f of y dy is equal to g of x dx. And then if we stick an integral sign in front of that, and we stick an integral sign in front of that, you'll see I get very quickly to that place that I got to at the end of the more complicated and precise way of doing it. So that's the quick way. So just to give two very quick examples of using that method to solve differential equations, why don't we try to solve the two differential equations we've just written down? So the last one I just wrote down was for the height of water in a vat, dH by dt is equal to 2 minus 3h. You can see this is a very simple example of a separable equation because there's actually no time dependence on the right at all. So what we do is we rearrange it in the way I've just said. We bring the h dependence down here. So we have 1 divided by 2 minus 3h dh is equal to dt. I'll put an integral sign there, an integral sign there. And if I can do this integral and I can do this integral, then I can solve this differential equation. Well, the right-hand side integral is the easiest one. So let's do that first. That gives us just, this is essentially the same as the integral of 1 dt, so that's t plus our integration constant. The left-hand side is a little harder. You can do it by the substitution method. You can make the substitution u is equal to 2 minus 3h, and if you're not confident in doing this integral, I recommend you make that substitution. Or you can spot what the right answer is if you're familiar with integration methods. In fact, the right answer here is minus a third times the logarithm of 2 minus 3h. And I really ought to put modulus signs there. I'm being technically correct. And this minus a third comes from the fact that you've got a minus 3 here multiplying the h inside the integral. So you need to divide through by minus 3 outside the logarithm. And you can easily check by differentiating this left-hand side. If you differentiate this left-hand side with respect to h, you get back what's inside the integral sign. So all that's required to do now is to rearrange this expression here. This is effectively a solution of the differential equation, but it might not be in the form that we want it to be in. And so a very simple rearrangement we can do is you can multiply through by minus 3 and get the logarithm of 2 minus 3h is equal to minus 3t plus, and I'm going to multiply this constant by minus 3. Well, multiplying a constant by another constant just gives you another constant. So I'm just going to call it c. It's not the same constant as that one, but it's still a constant, so that's all right. Now, if you have a solution to a differential equation which has got logarithms in, here's a tip. It's very useful often to call those constants, not just call it a constant, but just call it the logarithm of another constant. Logarithm of a, say. That helps you rearrange these things using your logarithmic rules. I've not done anything special. All I've done is replace one constant by another constant. The logarithm of a is still a constant. Now I can take this over to this side and I get the logarithm of 2 minus 3h minus the logarithm of a is equal to minus 3t. If you remember your rules of logarithms, if I've got one logarithm minus another one, I can write that as the logarithm of 2 minus 3h divided by a is equal to minus 3t. And finally, I want to rearrange this to get rid of the logarithm and turn the logarithms into exponential. So the exponential is the inverse function of the logarithm. So if I've got logarithm of something is equal to something else, well, we can write 2 minus 3h divided by the constant a is equal to e to the power of minus 3t. Okay, well, I'm nearly there now. I multiply through by my constant. 2 minus 3h is equal to a times e to the minus 3t. And then I rearrange this to make h the subject. So I end up with 3h is equal to 2 minus a e to the minus 3t. And I divide through by 3, finally. And so I get h is equal to 2/3 minus a over 3 e to the minus 3t. And that then is the solution to this differential equation. I might be interested in a particular solution where I know what the value of h is at t equals 0. So if, for example, h is equal to 0 at t equals 0, so the vat was initially empty when I started pouring water in, then it's very easy for you to check that a has got to equal 2. And so h is now equal to 2/3 into 1 minus e to the minus 3t. And so, as a function of time, h starts at 0, it goes up to a value of 2/3 and increases like so. That might remind you of the curve that we had for the capacitor. It's essentially the same sort of differential equation. And so finally, let me just give you a quick tip on how to solve another differential equation that we wrote down. So for the population dynamics of the bacteria on a petri dish, we had dn by dt is equal to some constant times n into 10 minus n. So again, this is a separable first order differential equation. To solve it, we bring our n dependence down here, we bring our t dependence up to the right, so we get 1 over n to 10 minus n dn is equal to k times dt. We put our integral signs there, and that's the way we're going to try and solve this differential equation. Now, again, you can only solve it if you can do these two integrals. The one on the right is very easy. It's equal to kt plus c. The one on the left is harder because that involves partial fractions. So the way to do this is to recognise actually that 1 over n times 10 minus n can be rewritten as a tenth of 1 over n plus 1 over 10 minus n. So that's, to do this rearrangement, you have to use your methods for partial fractions. And so finally we do this integral here on the left, and we would end up with a 10th of the logarithm of n minus the logarithm of 10 minus n is equal to kt plus, well look, here we've again got a situation where we've got logarithms floating around. So it might be useful to write c in terms of constants involving logarithms. So actually we've got a 10th of logarithms on the left hand side. So my tip here is to write the constant c as a 10th of the logarithm of a here. And you can play around with that. Now that's kt and that's a plus sign. I'm not going to finish off rearranging this one round for you. That's the solution of this differential equation in a particular form, but you need to rearrange it to get it in the form n is equal to some function of time. I'll give you a clue as to what that looks like when you've finished. So the final equation you should end up with is n is equal to 10 times a e to the 10 kt divided by 1 plus a e to the 10 kt. So what does this final solution look like? Well, if you were to plot it out, you'd find that it solves a problem with the rabbits. The rabbits go off to infinity as a function of time. Now, this one doesn't go off to infinity as a function of time. It starts off increasing exponentially, but there's a point at which it reaches a maximum, and that maximum is at n max. In this case was equal to 10, and you'll find that this equation tails off and just gradually approaches that maximum value of n. So if you were to plot this out as a function of time, that's what you'd get. Okay, so I hope that's given you an idea of why you might want to use differential equations, a few examples of where they're used, a few examples of how you might go about solving them.